If you're just tuning in, I'm already pretty deep into reverse engineering smart meters. The goal I have now is to create a little device that I can attach to any smart meter that will allow me to read out the firmware, bypassing whatever security protections exist.
Anybody remember how to defeat an electronic keypad?
Oh, don't even joke about that, Martin. Those things are impossible.
Why, you might ask? So that you can buy your own smart meter, attach this little device to read out your own copy of the firmware. Think of it like a very special programming cable. It doesn't matter whether the chip wants you to have a copy of the firmware or not. It allows you to get a copy of the firmware for any supported smart meter, so you can reverse engineer it yourself. That's what I want to build over the course of the following videos, a way for us to pull back the curtain on how these devices operate. I've been spending a lot of time here on smart meters and software-defined radio. You can follow along by watching my other videos to receive and decode radio transmissions from the smart meter network. You can also contribute on GitHub, the wiki, or in Discord. There's links down in the description. When it comes to firmware and software though, I can't share any of that online. You see, all the real juicy information is hidden inside these chips. The software that runs the smart meter network is really what we need to analyze. The truth about how secure these devices are and what vulnerabilities exist is locked away. The challenge is, even if I can unlock this chip and get a copy of the firmware, I can't share it with you for the same reason I can't share copies of any other software. But what if there was a way around that? What if I created a special interface cable, kind of like a mod chip used for gaming consoles, that when attached to a smart meter allows you to access a copy of the firmware? Now I can't accept funds for this mod cable directly.
Oh, excuse me. I'll handle that for the mayor.
Hey, what is this?
I'm gonna
What is
handle.
this? What is this?
I don't know.
Who are you? I don't know you.
But what I can do is make the design open source and connect you with my smart meter supplier. You see, if you purchase your own smart meter and I show you how to extract a copy of the firmware, we can both look at it and reverse engineer together. Over the next few videos, what I am going to use is a technique called glitching, which confuses this little microprocessor so it gives us free access to memory locations that are supposed to be locked away. One of the great things about digital electronics is repeatability. They're very good at doing the same thing over and over and getting the same result, but only when you operate these devices within very specific parameters. As you move to the edges of these parameters, interesting things start to happen. Now, the specification documents for these components don't tell you what sorts of interesting things will happen. They just tell you not to go there. Take for instance page 1156 from this microchip datasheet. It says, and I quote, "Large and fast supply variations may lead to unpredictable device behavior." This warning is here for the engineers designing products using this part. It lets them know that their power supply design should be free from fluctuations and they should have an adequate amount of decoupling capacitors near the power supply pins. On the other hand, this device is called the ChipWhisperer, and it is a tool that will allow me to easily generate power supply fluctuations, which in turn will cause the processor to malfunction in useful ways. You see, it's incredibly easy to cause electronic devices to malfunction. But getting them to malfunction in a way that benefits us requires a precision attack. In order to figure out the best place to attack the processor used in this smart meter, I'm going to use this development board, which contains the same processor. After some reading in the datasheet, I saw there are multiple supply voltages, and the core voltage that runs the processor is separate from other supplies, like the input-output circuitry. It's a lower voltage generated internally by the processor, then fed out of a pin and back in. This will be an ideal place for us to take control and craft our very own precise fluctuations. The theory is an unstable supply voltage will temporarily confuse the chip, but not so badly that it reboots. To do this, we need a test program, some code doing something incredibly simple and prone to failure should an unpredictable event occur. This simple loop is just the thing. All it does is count up to 5 million over and over. If for some reason it doesn't count up to 5 million though, it will tell us by printing glitched on the screen. If it reboots, it will also tell us so that we can fine-tune our glitch parameters. As you can see in this reference design, the VDD core part of the power supply is separate and where I have chosen to attack. This wire is soldered to the VDD core power plane, which also connects to pins 11, 44, 63, and 89 of the processor. The ChipWhisperer is connected to the other end, and a small Python script is used to set its parameters. It basically boils down to this section where I define how long the ChipWhisperer should short this power supply to ground. Now normally when we think of something shorting out, it involves sparks, and it might not work afterwards. But in the case of the glitcher, the length of time we short the power supply out is so incredibly small that the voltage doesn't even fall to zero. Due to glitch timing, length of wires involved, and capacitance on the circuit board, the voltage just dips down into the unpredictable region the datasheet told us about. If we put it all together, executing this part of the script will tell the ChipWhisperer to send our glitch, and this terminal window will tell us if our glitch was successful or if we went too far and caused a reboot. This view of the oscilloscope will let us see what the power supply looks like when the glitch is applied. I'll start with a glitch that's a bit too long and you'll see it reboot. Adjusting the glitch parameters is mostly trial and error, but now that I have it dialed in, it causes a fault almost every time. And when I say trial and error to figure it out on this board, it didn't take me more than a few minutes once I had the wiring hooked up. It's just a matter of guessing values, finding values where it reboots, then decreasing slowly until it doesn't reboot and consistently generates a fault. The key is a test program that's looping like this, which lets you easily see when you end up in a fault condition. Now I have to admit, it was extremely exciting coming up with a theory of where to glitch this processor, and then actually having it work. But that's just the beginning of the journey to create a mod chip-like cable that will let me access any smart meter firmware. In the next video, I'll apply this glitch while trying to access restricted parts of the processor, which were locked down by the manufacturer. If you want to come along on this journey with me, make sure to subscribe and check me out on Twitter and TikTok. I share more raw content there about what I'm working on and interesting things I find along the way. If you want to join in on the reverse engineering, check out the Richessum Wiki, stop by the Discord channel, and say hi. Thanks for watching.